Jupiter has a long history of surprising scientists, going all the way back to 1610, when Galileo Galilei discovered the first moons outside of Earth. That discovery changed our perception of the universe, and recently scientists discovered something in Jupiter. What did they discover? Hi guys, welcome back to Not Alone, your space buddy. Today we'll look at what scientists discovered Jupiter doing, so stay tuned until the end, and if you're new here, don't forget to subscribe to our channel and hit the bell icon, which is completely free. Let's get started. Huge, swirling cyclones are raging on Jupiter's poles. They are known to be caused in part by polar turbulence and convection. Another phenomenon that isn't fully understood is why some of these massive cyclones form neat geometric patterns that remain stable for years at a time. According to Vice.com, astronomers have been puzzled by this phenomenon for some time, and at Jupiter's poles, enormous cyclones swirl in neat geometric patterns that remain stable for years at a time, a phenomenon that scientists say hints at the need for new physics. Jupiter has dozens of moons orbiting it. Jupiter has rings as well, but unlike Saturn's famous rings, Jupiter's rings are very faint and made of dust rather than ice. The well-known Great Red Spot on Jupiter is a gigantic storm that is bigger than Earth and has been raging for hundreds of years. In addition to cyclones and anticyclones, Jupiter is well known for its distinctive belts and zones, which are white and reddish bands of clouds that wrap around the planet. The bands are separated by strong east-west winds blowing in opposite directions. Juno previously discovered that these winds, also known as jet streams, reach depths of roughly 3,200 kilometers. Researchers are still trying to figure out how jet streams form. Juno data from multiple passes reveal one possible clue. Ammonia gas in the atmosphere travels up and down in remarkable alignment with observed jet streams. A group of space scientists from several US agencies, along with colleagues from Italy and France, used a model to explain the resilience of a hurricane orbiting Jupiter's poles. The group analyzed images captured by the Juno spacecraft and used what they learned to explain why hurricanes last so long in a paper published in the journal Nature Astronomy. Describes the process of developing the Shoal model. NASA's Juno spacecraft entered orbit around Jupiter in 2016. The Juno probe was launched on August 5, 2011 and arrived in Jupiter's orbit on July 4, 2016. It is the most distant space probe ever powered by solar arrays. It orbits the planet from pole to pole rather than around the equator like other such probes. Researchers were surprised when the probe began sending back images of the planet from this new vantage point. Not only was there one cyclone at each pole, but they were both surrounded by other cyclones. More images of the poles have emerged over time, and researchers who study them are still astounded by the cyclone's stability. The original cyclone is still standing today, unchanged in shape. Such behavior is of course unheard of on Earth. A cyclone forms, moves for a while and then vanishes. Such behavior enabled researchers to find logical explanations for their findings. Photographs taken near the planet's north pole showed 8 cyclones circling a central cyclone just above the pole. All 8 are arranged in an octagonal pattern and are close together, roughly equidistant from the central cyclone. Antarctica has a similar configuration but only has 5 pentagon-shaped cyclones. The researchers tried a new approach in this new endeavor to explain why hurricanes stay in place for so long and how they stay in place without changing position or shape. The team led by Andrew Ingersoll, who serves as Earl C. Anthony Professor of Planetary Sciences at the California Institute of Technology, was responsible for analyzing imagery and other data from Juno's probe, particularly wind speed and direction. They then used what they had learned to build a shallow water model, which led them to believe that there was an anticyclonic ring of wind moving in the opposite direction of the cyclone, keeping it in place. That could be true, but the team couldn't find any evidence of convection to explain how the heat fueled the cyclones. We acknowledge that more research is required to fully explain. Since 2017, the Juno spacecraft has observed a cyclone at Jupiter's north pole, surrounded by 8 smaller cyclones arranged in a polygonal pattern. The researchers wrote in their study, "It is unclear why this configuration is so stable and how it's maintained. The polygons are individual vortices that comprise them have been stable for the 4 years since Juno discovered them," the team added. The polygonal patterns rotate slowly or not at all. In contrast, Saturn has only one vortex, a cyclone at each pole. To get better understanding of how the polygons form and then remain so stable, Ingersoll and his colleagues used Juno's Jovian Infrared Auroral Mapper, that's GRAM instrument, to measure the winds and dynamics of the extraterrestrial tempests. GRAM can detect details of the poles at scales of 180 kilometers, revealing a torrent of winds that act as a kind of brace for the cyclones, which is critical to their stability. However, what the team didn't notice in their observations is just as important as what they did. In contrast to previous research, the researchers noted that they did not find the expected signature of convection, the process by which heat is transferred through churning fluids. Ingersoll and his colleagues noted in the new paper that a parallel study of Jupiter's south pole vortices focusing on vorticity and stability represents a step in the right direction. These stunning geometric storms are just one of the many mysterious processes on Jupiter that scientists hope to investigate with missions like Juno and the recently launched James Webb Space Telescope. Jupiter, as the largest planet in the solar system, has no shortage of strange and unusual phenomena, but it can also serve as a model for understanding similar observations on other planets, including Earth. In a 2019 NASA statement about previous research, Cheng Li, a Juno scientist at the University of Michigan, Ann Arbor, and a co-author of the new study, said, "These cyclones are new weather phenomena that have not been seen or predicted before. Nature is revealing new physics about fluid motions and the workings of giant planet atmospheres," he said. "We're starting to understand it through observations and computer simulations. Future Juno flybys will help us refine our understanding even further by revealing how cyclones evolve over time. The findings of NASA's Juno probe previously released provide a more complete picture of what's going on beneath the clouds. Juno data show that Jupiter's cyclones are warmer at the top with lower atmospheric densities and colder at the bottom with higher densities. Anticyclones are colder at the top but warmer at the bottom because they rotate in the opposite direction. These storms are also much taller than expected, with some extending 100 kilometers below the cloud's tops and others, including the Great Red Spot, extending more than 350 kilometers. This surprising discovery shows that vortices extend beyond the regions where water condenses and clouds form and below the depth where sunlight warms the atmosphere. Juno data also showed that, similar to hurricanes on Earth, these cyclones want to move poleward, but cyclones at each pole push them back. This balance explains the location of the cyclones and the different numbers at each pole. So they might be there in the future too, and scientists can discover new physics from the cyclones. This concludes our video. If you liked the video, don't forget to give it a thumbs up and share this with your loved ones.